Hi, we are going to discuss a very interesting technique to sort values. It is called RadixSort. RadixSort is a very interesting sorting technique because it doesn't require comparisons. In other words, in this technique, we are not going to compare two values at a time. Also, we're going to notice, and we will discuss this at the end of the video, that not all type of data are suitable for this technique. The technique is very simple. Essentially, we're going to take a look at the least significant value of the numbers or words or whatever objects we are given, and then create groups what we call buckets. Once we create the first set of buckets, then we regroup the values using the next significant key, and that gives us a second group, and then we're going to have a third group and then a fourth group until we have all the values sorted. Things will become more clear as we do the following example. Let's assume that we're giving the numbers that you see on the screen, which are in random order. The thing to notice is that every one of these numbers intentionally has exactly 3 digits. We will see why this is important in a couple of seconds. So the first step is to create buckets, and I'm going to create buckets by using a parenthesis. The first bucket is going to be created using the criteria of the least significant value, which in this case is the rightmost digit. The very last digit is the least significant value. So my first group is going to contain all the numbers that end with 0. And as you can see, there are no numbers that end in 0. So next group is going to be the numbers that end in 1. And I'm going to see, or we see, that 341 and 141 are 2 numbers that end up in 1. So my first group or bucket is going to have those 2 numbers in the order that they were given to us. In other words, 341 is the first one, followed by 141. There are no other numbers. So now I'm going to create the next group would be the numbers that end with a 2. There are none. Then the numbers that end up with a 3. There are none. And so on and so forth. So the next group would be numbers that end up with 4, numbers that end up with 5, numbers that end up with 6. Finally, we have 126, 636, and 416. So I'm going to create a group with those 3 numbers in the order that they were given to me. Okay? And that's the group of the numbers that end up in 6. Next, the group of numbers ending up in 7, none. And then the numbers that end up with an 8, and I clearly see that there are 2 numbers in there, 328 and 128. I should repeat the process creating buckets for the numbers ending with 9, and that will be it. Okay? So there are none. So I'm done with the first iteration of the algorithm. So now I have 3 groups. Okay? And apparently these are not in any particular order, but we'll see how the technique works. The next step will be to regroup the numbers as I have them using the next significant digit, which in this case is the middle number. And I'm going to do the same thing. So the first group is those numbers that have a 0 in the middle. There are none. Next group, numbers that have a 1 in the middle. And I say that 416 is the only number that has a 1 in the middle. And there are no other ones, so I'm done with that group. Next group, numbers with 2 in the middle. And I see that I have 126 and 328 and 128. So those are the 3 numbers that have 2 in the middle. My next bucket will be numbers with 3 as their second digit. So I see that I have 131, 636. So I'm going to write in here 131 and then 636, and I'm done with that. Then the next bucket will be the numbers that have 4 in the middle, and I see that 341 satisfies that criteria and is the only one. So I'm going to copy 341. And then I'm going to see if I need a bucket for the numbers that have 5 on the middle. There are none. 6 on the middle. There are none. 7, 8, and 9. So I don't need any more buckets. Okay? So that's the second iteration of the algorithm. And again, it's not obvious that these numbers are in increasing order. Now I'm going to apply or regroup one more time. And you guessed, now we're going to use the leftmost, the first digit that I see in here. So the first group, okay, will be the numbers that start with 0, they're none. Second group, the numbers that start with 1. So let's pay attention. 126 is the first number, so that's the first number that I insert into that group. The next one will be 128. So I need to copy 128 here, and then the next one will be 131, so I'm going to put 131 there. And those are all the numbers that I have that start with 1. My next group, numbers that start with 2, they're none. Next group, numbers that start with 3. So 328 and 341. So I'm going to put in here 328 and 341. Those are all the numbers that start with 3. Next group, numbers that start with 4. There is only one, 416. So I'm going to write 416. I'm done with that group. Next group, numbers that start with 5. There are none. And I see that these numbers start with 6. So that will be in the bucket of the numbers that start with 6, and I'm done. And now we can see that these numbers are in increasing order. So my last step, once I finish sorting, is simply to get rid of the group and just copy the numbers in the order that I see them. So it's 126, followed by 128, 131, 328, 341, 416, and finally 636. And now you see that the numbers are sorted in increasing order. That is how RadixSort works. So let's do some analysis. First thing to notice is that we didn't compare the values. We didn't ask the question, is this value greater than or less than the other? The second very important aspect of this technique is that we didn't swap. We didn't insert values here and then we move them down. We simply created groups or buckets as we went through the algorithm. Therefore, the expected running time is n. That means it's directly proportional to the size of the data. As a matter of fact, the numbers of times that I need to apply the algorithm depends on the numbers of digits. In other words, if the original numbers, everyone will have 6 digits, then I will have to apply the technique 6 times. If the numbers have 11 digits, then I will have to apply the technique 11 times. So the n is directly proportional to the numbers of digits on the data. This is a lot faster than other sorts, which are called quadratic sorts. Now, let's try a different example. Okay, let's try these numbers, which intentionally, as you can see, they are already sorted. They are in increasing order. So the numbers of steps will be the same, 3. Why? Because every number has 3 digits. So I have to create groups using the least significant digit, the rightmost, then the digit in the middle, and then the digit on the leftmost positions. So that's 3 passes of this technique. I'll do it nevertheless. So the first group is the numbers that end up with 0, and I see that 100 is the only one. The second bucket is going to be the numbers that end up in 1, there are none. Then next, numbers that end up in 2, numbers that end up with a 2, there's 632, okay? Then the next bucket is numbers ending in 3, okay? 843, 843. Next bucket, numbers ending in 4, there are none. Next bucket, numbers ending in 5, 235. My next bucket is the numbers ending in 6, and I see that there is 376. And my next group is the numbers that end up in 7, and I see that there are 317, 587, and 687. So there are 3 of them. So it's going to be 317, followed by 587, followed by 677. And then I'm done because there are no numbers ending in 8 or 9. Then what's going to happen next? What's going to happen next is the same thing. I'm going to create groups now using the number on the middle, which is the next least significant key in this, the number in the middle. So numbers that have a 0 in the middle, 100, and there is no other one. Now numbers that has a 1 in the middle, the only one is 317. Numbers that has a 2 in the middle, there are none. Numbers that has a 3 in the middle is 632 is the first one that I find. 235 is the next one, and we are done. Numbers that has 4 in the middle, 843. Numbers that have 5 in the middle, there are none. Numbers that has 6 in the middle, there are none. Number that has 7 in the middle, I see 376 and 677. So 376 and 677. And then numbers that has an 8 in the middle, I see only 587. And then there are no buckets needed for numbers that have 9 in the middle. So that's the end of the second pass. And now I'm going to apply this a third time. And I'm going to use the leftmost, which is the only key I have not used. So the first group, again, is numbers that end up with 0, there are none. Numbers that end up, that start with a 1, so that would be 100, right? Then what is the next bucket? The numbers that start with a 2, and there's only one, 235. The numbers that start with 3, so I have 317, okay, followed by 376. Next bucket, numbers that start with 4, none. Numbers that start with 5, there is only one, 587. Next bucket, numbers that start with 6, 2, 632 and 677. So I'm going to put there 677. And my next bucket, as you can guess, is number that start with a 7. There are none. Numbers that start with an 8, 843. And I'm done because there are no numbers that start with 9. And then I simply now get rid of my buckets, the groups. So I have 100, followed by 235, followed by 317, 376, 587, 632, 677, and 843. And those numbers are in increasing order. So the conclusion is that even when the numbers are sorted, I'm going to go through 3 iterations of the algorithm because my numbers have 3 digits. So it still is directly proportional to the size of the data. So that's for numbers. What if we have other values like letters? Then the criteria will be the same thing. I'm going to create buckets. And in this case, I'm going to use the letters of the alphabet. And I'm going to start with the least significant, which is the rightmost. So I'm going to be taking a look at the very last letter in each of these values. So first group is letters that, or words that end up with an A. The next group, words that end up with a B. And I see that I have CCB. Okay, there is no other word that ends up with a B, so I'm done with this bucket. Then there is the group of words that end with a C. There are none. Words that end up with a D. There is one, A, B, D. Okay, and there is nothing else. So my next bucket is going to be words that end in an E. There is one, F, R, E. And that's it. And then I continue through the English alphabet, so you can see how I'm ordering these words. So the next group will be MLM, and it doesn't have any other one. And the next group will be GTY. And my final group will be the only word that is left, which is X, Y, Z. So again, I use the rightmost letter to create the groups. That's the first iteration. I have created these groups. Now I need to apply the same technique, creating new buckets, regrouping using the next key, the next significant digit, which in this case is the letter in the middle, the second letter. So the first group is going to be all those words with A on the middle. There are none. Then words with B on the middle. There is A, B, D. And that's it. The next group, words with C in the middle, C, C, B. That's the only one. Words with D in the middle. There are none. Okay? And then E in the middle, F in the middle, G in the middle, so on and so forth. I continue through the English alphabet. The next group would be MLM. There is no other L. And then the next group will be the words that have R in the middle, and there is only one, and that's the FRE. My next bucket will be, again, going through the alphabet. I'm going to S, there is none, T, and I find G, T, Y. And then the last word is going to be words with Y on the middle, which happens to be X, Y, Z. And that's my second iteration. Then I repeat the technique for the last time because there are only 3 letters. And I'm going to start with the first character, the first letter in each word. So words that start with A, well, obviously A, B, D, and that's the only one. Next bucket, words that start with B. None. Words that start with C, 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 B. There's nothing else. Words that start with the next letter in the English alphabet, it will be FRE. So I need to create a bucket for those 2, right? FRE. And then the next bucket is GTY. Then the next bucket is going to be MLM. And my last bucket is going to be, obviously, XYZ. And now at this point, I'm done because I only have 3 letters that I can use to sort. And then I can create the groups, which are A, B, D, C, C, B, FRE, GTY, MLM, and XYZ. And obviously these 3-letter words are in alphabetical order according to the English alphabet. So I can use this technique to sort numerical values, I can use it to sort words, and I can use this to sort other type of data. But obviously not every type of data can be sorted. So I'm going to give you an example, and I'm going to not do it, but think about a deck of cards. That's a very unusual set of data. So what kind of data, if we create an object, what kind of data do we have for each card? Well, each card will have a color, right? And there are 2 colors in the deck of cards. And then each card is going to have also a suit, and then we know that there are 4 of them. And each card could have a value, and there are 13 values. So one approach could be, if you give me a deck of cards which are not sorted and ask me to sort it, I could start by saying, I'm going to sort them by using colors, in which case will give me 2 buckets. What I will realize is that the numbers of values in each of the 2 buckets is way too many. It's not easy to sort, not even visually. So my next approach is to use the suit, and that will give me 4 buckets. And again, if you do the math with a deck of cards, that means that every bucket is going to have 13 values. And that, again, may be a little bit too much for me to sort by hand or visually. So what do? I create 13 buckets based on the values. What are the values of the deck of cards? Obviously 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King, and the Ace. So now I have 13 buckets. And the worst scenario would be that each of these buckets will have 4 cards in it. And because they have colors and they have suit, it will be very easy for me to say, oh, I have all the cards that I need, or I have missing cards or duplicate cards. So what I'm trying to illustrate is first that we can use this technique to use some sort of data that it doesn't apply to increasing or decreasing order criteria like words and numbers. Also that the same data, like in the case of the deck of cards, can have different criteria. In this case, you can use buckets by color, buckets by suits, buckets by values. Obviously, one of those is going to be more efficient. In this case, again, buckets by value. So let's analyze the RadixSort. As pointed out through the discussion, not every type of data is suitable for this technique. But the thing to realize is that this is different from other sorting techniques in the sense that we do not compare one value with the rest, and we don't exchange the positions of the value. We simply regroup, creating buckets, and that leads off to an expected running time of n, which means it's directly proportional to the numbers of buckets and size of the data. And this is much faster than anything that is n squared, which we have studied in the past. If you have not watched the videos, there are 3 videos in insertion sort, selection sort, and exchange sort, which are very different from RadixSort.